Good morning to you all. Okay, so far we have 4 participants, okay, and others are joining in. It's good to see, admitting all of you. Yeah. Okay, so firstly, can any one of you confirm if you are able to hear me? Okay, then I'll proceed further.
Yes, sir.
Yes.
Okay, that's good. All right, so what is left to do now? Would you like me to go over the bolt analysis, or are you guys okay with it?
Just roughly, sir.
Okay, roughly would mean all of it, isn't it? Okay, right. So let's see, and okay, maybe I'll just use this slideshow, right? So the first things first, just recapping. So the last thing I said was regarding the bolt PCD, right? Which means the bolt pitch circle diameter. So if I refer to my drawing again, a pitch circle diameter would mean if I draw a circle and the circumference of that circle should pass through all the 4 centers of these bolt holes you see here. So that's the pitch circle diameter. Now that is based on your estimation. So now you have completed all the analysis, you know the dimensions for the key, you know the dimensions for the hub, and you also know the dimensions of the web, right? Okay. In terms of the web thickness, right? How thick or thin is it? But in terms of its diameter, right? That is how would I say? That is based on your estimation. Okay. Are you getting me when I say the web diameter? What would be the web inside diameter? Web is whatever you are able to see in red. Okay. Maybe I'll just turn off the others. So yeah, looking at it, so the inside diameter of this web here is equal to the outside diameter of the hub, right? And now for the outside diameter of the web, that is entirely up to you, right? How big or how small, okay? Keeping in mind where would you place the bolt holes, right? So in what would I advise in this case is if you can choose, let's see, you can choose anything between 200 to 230, okay? So just so that you don't go stray with your dimensions, right? I'm talking about the outside diameter of the web here. So you can choose anything between 200 or to 220, okay? So then again, you will estimate how further inside this PCD would be, okay? So for example, let's say if I choose a web outside diameter of, let's say 220, then obviously the PCD has to be less than 220. I hope you're able to get me, right? Okay. Now PCD would mean the diameter of, okay, if I, from one end to the other end, if I measure the length across, which is basically the PCD, when I say one end, it means the one end of the bolt center to the other opposite end of the bolt center. That would be obviously the PCD, right? So that's the pitch circle diameter. Okay, so you can choose any value less than the outside web diameter. Yeah, I hope that wasn't too confusing. So that's what you will do first, right? So determine the PCD for bolts. Okay, so in this case, what you guys are determining is the number of bolt used in this case. After that, the formula is the same. Okay, so everywhere in all our analysis, we are using torque, starting off with the torque. So torque is equal to, this time it is used shear force. Okay, so you have a flange coupling. Okay, you have two of these and they are held in place. Okay, you have two of these, they are held in place together with bolts. Okay, one side is connected to the motor, the other side is connected to the gearbox, right? So what happens is, as soon as the system starts to operate or is in operation, okay, so because they're both of the flanges are held with bolts, okay, so if your design is not proper, the bolts would shear off or break off, right? So that's why shear force is used in this case. Where were we? Okay, so therefore torque is equal to Fs divided by R. Now, what would be R in this case? Any guesses?
The PCD radius.
Exactly. It will be essentially half of the PCD, right? Okay. So now you make the shear force subject of the formula. You know the value for the torque. You know the PCD you have chosen. Okay, so that's specifically to all your assignment problems. So find the shear force. After you find the shear force, okay, I'm not noting anything down here because on the calculation sheet, because everything is pretty much similar to the other analysis, right? Okay. Maybe I'll just control C. Volt analysis. Okay, so this is the next step which you guys will be doing. And this is what we are going over at the moment. Anyway, so right. So now what happens, it says determine the number of required bolts. Okay, so your formula is still the same. So this is the TS is the bolt working shear stress. Okay, and in this case, it's given in Newton per meter squared. So there was a question on one of the forums, discussion forum, okay, about the dimensions. So be consistent with the dimensions, right? So here, so we have listed down all the details regarding the bolts, okay? So since we said the bolt would shear off, okay, if not designed properly, so you could use the shear working stress value, right? Whatever value is given here. And I did tell you in the very first class, how do you find these two values? Okay, if you're unsure, please refer to the videos. Okay, so you'll use the shear working stress value, input it in here. Okay, and you know, just from your previous calculation, you know the shear force. B here means the number of bolts. Okay, so B is the number of bolts in the pitch circle bolt pattern, right? Multiply by area of bolt. Okay, AB is the area of the bolt. How would you find the cross-section area of a bolt? Or how would you find a bolt is a cylindrical object? Okay, assuming for simplicity's sake. So for a cylindrical object, how would you be able to find the cross-section area? Yes, anyone? Any suggestions?
So is it area is equal to 2 pi r height plus 2 pi r squared?
Plus, um, not really.
Okay.
So if you Control C.
Sandeep,
Yes.
The cross section of the cylinder would obviously show a circle. So would you use pi r squared? No.
Yep, exactly. Right? Yes, that's very much correct. Right. So cross section of a cylinder, A represents a circle. So you find the area of a circle. Area of a circle is equal to, sorry, symbol is pi r squared, isn't it? Yeah. Now this r here, what do you think this r would be? What does it represent? This r would mean what? Is equal to the radius of the bolt, right? So you got it. Now again, your assumption. Now this radius you would assume. Why do I say that? Because, okay, so if you look at this calculation, right, after that it says round the evaluated. So if you get a decimal or if you get a fraction, so obviously to determine the number of bolt, which is B, you have to round it up to a whole number, right? So, and then it says here to review. So you know that area is equal to pi r squared. That r in that area is equal to the radius of the bolt. That you'll have to assume. Okay. So if you get a value for B which doesn't look okay, so you'll have to go back again and change the value of the radius of the bolt and then do your calculation once more. So what happens going from this equation to the one below it, you're making the number of bolt the subject of the formula. The shear force you know from your previous equation divided by the shear stress, the shear working stress for the bolt you are given in your assignment question, multiply by the area of the bolt. Area is pi, multiply by r squared. R is the radius of the bolt. So the only variable for you to solve will be B, number of bolts. Okay, so just by looking at this drawing, pretty much in my case, I have assumed 4 bolts. Okay, so the value for B is equal to 4, right? So if I get a number, if I do my calculations and I get a value for B as 3.4, so I'll obviously round it up to the next whole number, right? So in my case, it's 4. So now, is that good enough? Was that easy for you to understand? So I've just pretty much copied everything from the notes and written it down here. So making your work easier, just determine the number of bolts. Okay, you could also work your way the other way in the terms that you know B, which is the number of bolts. Let's say you use B as 4, and then you make R the subject of the formula. Then you find the radius of the bolt. In other words, you're determining the size of the bolt. Okay. Any questions? Okay, now I'll give you a good.
Sandeep,
Yes, yes.
is there any limitation to the number of bolt, or it can be like from your calculation?
You mean the value for B?
Yeah, like is there any limitation like in standard form?
Not really, but it should be something which looks practical, right?
Practical, right? Yeah,
Okay, so if you have one bolt, that is not practical, right? Even two, you know, having just 2 bolts would put a lot of stresses on the bolt, because keeping in mind how fast the shafts are rotating and subsequently how fast this whole flange coupling will rotate. So 3 is okay, 4 is also okay, 5 would also be okay. Yeah. So, but yes, you don't just write that B is equal to 4. Okay, you have to show your calculations. How did you get to 4? Okay, it's just very, very basic calculations. There's nothing hard. There are only 2 places for the bolt analysis. You are making assumptions. The first is determining the PCD. I should probably put this down here. so that none of you guys get confused. All right, there you go. And whenever I put a hashtag, that means that is what you're required to do, right? In terms of calculations. Who was that who asked me the question? Was it?
It was me.
No, let's see. Am I able to get your name? Was it Joel?
Yes.
Okay, yeah. So does that answer your question?
Yeah.
Okay.
Thank you.
So there are 15, excluding me, there are 14 of you. Okay. So start from the beginning. I'll give you time before I discuss about what drawings you need to do. Okay. So I hope you have started with your calculations. So if you have any questions, now is the time to ask. Okay. Right. I'll give you the freedom to do that. So you do have the freedom to do that. So we are not able to see any one of you. Okay, feel free to unmute yourself and ask questions. Right. This is the best time. Okay. If I'm not able to clarify, then obviously your other colleagues who are online would be able to provide you suggestions. So now you guys have the mic to speak. Okay, so I'm not getting any questions from you guys. So my assumption is that all of you are on point with the calculations. All right. Anyways, I'll just go over this once more. Okay. So 2 parts to your assignment. The first part is design analysis. So, and the second part is drawing generations. You cannot go to part 2 without completing the analysis. Right. The reason you need that is because through the analysis, you would be able to, oh, there's a chat. Sir, could you go over the balances again? My Zoom wasn't able to connect. So okay. Right. So once I finish with the, at the end, once again, I'll go over the bolt analysis. Right. So you can't do drawings without knowing the dimensions. Right. Okay. That is important. And so yes, let's see. So when it comes to the design analysis, you are given a calculation sheet, which has a standard view. Okay, it has the project title, the authors. So I believe you're doing this in pairs. So write your name with your ID and your partner ID and name. Okay, the date which you probably started with the assignment. Okay, not really important. And yeah, if you can just probably include somewhere who is your tutor, okay, or who is your teaching assistant. Okay, so we are aware which session you belong to. Okay, but not really important at this stage. And the page. Okay, so in my case, 1, 2, 3, 4, 4 pages I have used. So this will be page 1 of 4. Right, the next one will be page 2 of 4. So start with the overview. Again, this has to be in your own words. Overview is basically like a summary of your entire calculation report, right? So if someone else picks up your report, he or she should be able to understand straight away okay, what this report contains, what information is provided, and what information is this author trying to determine, right? Okay, so we have said, or I have said that we are doing analysis, calculations together with assumptions for a flange, to design a flange coupling, okay? And what is the purpose? The purpose is to transfer or transmit power from one shaft which is connected. So you could make this more precise, right? I haven't said here that the power is transmitted from the motor to the gearbox. Okay, you could add this here as well. And the coupling is to connect it. Oh, anyways, it says here a drive motor to a gearbox. Okay, so please go ahead and write this in your own words. Okay, not hard at all. Assumption, okay, we are assuming that there are no impact loads. Okay, the only load acting on the system is due to the torque which is generated, which we'll come to later on. Materials used, okay, really important. Just like in any textbook, okay, you list down the knowns first. So that is what we are doing here. For the shaft, we are saying that there are no calculations required. Okay, moving ahead, you could pretty much keep this the same. It will be pretty much the same for all of your reports. Okay, for the coupling, it's made out of cast iron. So what is the tensile working stress? Okay, and it is a good idea at this stage to understand what it means by working stress, ultimate stress. Okay, and if you're not sure what do they refer to, then what happened here? One of these slides here, okay, it pretty much explains to you, okay, using material properties, what is the UTS, okay, what is the working stress, what is the yield stress, okay. So anything below the yield stress is you are within the working stress range, okay. Then you have the yield stress followed by the ultimate UTS, and after that there is failure, right? Okay, it is different for different metals. Anyways, going back to your report, so you list down all the knowns. So for the coupling, it's made out of cast iron. For the key, it wasn't specified, so please do note this, that the key is made out of steel. And for steel, you also have to note down its tensile, compressive, and shear stress. Why are we noting this down? Because we are using this later in our calculations. And coming to the units, okay, so be consistent with your units, right? So it's 8. I have used, it says in your assignment, where is it? Here. So either you can use working stress in meganewton per meter squared or Newton per millimeter squared, right? So for cast iron, it's 8. So it's either 8 meganewton per millimeter squared, okay? So you can always be consistent with your units, right? And yes, and all of you have learned to use SI units. So if you want, you could use that all the time.
So just a question.
Yeah, carry on.
So will we be using the ultimate tensile stress and the yield stress of the balls, which is given here in the analysis?
No.
No. Okay.
No. The reason you will be not using it is because you would have noticed that in all our calculations we are using the working stresses. Reason being, because it says here, yes, because it includes the factor of safety, right? Okay, so meaning all the calculations which you are doing, and at the end, the values you will get, which you will use for your design in drawings, will include the factor of safety. So your factor of safety would be pretty much greater than 1 in this case. Okay, so you would say your design is safe, right? Okay, and what else is there? So I've just made changes to this one. Okay. See, but don't be too confused about the units. So it ultimately it determines the values you get, right? So here we are. So after getting all that, starts with the torque calculation, right? So as for the torque calculation, you're given the power this formula is provided to you in this PowerPoint slide. So 2 pi nt over 60. So this is where the units come into play, right? Okay, so power, you convert it into its standard units, which is watts, okay? So convert kilowatts into watts. And I believe the rotational speed was given in revolutions per second. So convert it to revolutions per minute. And then once you use SI units, automatically the value for torque you will get will be given in Newton meters, right? Okay. So there you go. And after that, you start with the key analysis. So for the key analysis, you're given the width and the thickness. When I say given, it is given in the last page, okay? So using the shaft diameter, we were able to determine the width and the thickness of the key. So you use that in your calculations. So only thing you need to determine is the length of the key, okay? So we assume that the key will fail in shear. So to torque, you are aware, and you use the radius of the shaft. So always torque is equal to force times distance. Distance means from the center to wherever that force is acting, to the point where that force is acting. So that's how we determine what R is for all our analysis, right? And so key is experiencing shear stress. So stress is equal to force over area. So the area part of the equation, you break it down into the length of the key, width of the key, and then you find the length of the key, right? Once that is done, we did the hub, okay? We'll call it the hub analysis, right? So not to confuse anyone. And similarly, for the hub, you have to determine at which point the hub breaks, okay? That's why we did RA. IA means assumed radius, okay? So, which is the radius of the shaft plus half the key thickness plus half of the hub thickness. This part I said you could assume anything between 6 mm to 9 mm, right? So that's your assumed radius. Got it? Okay. So once again, torque comes into play. So we are assuming that the hub will fail due to tensile force. That's why Ft. So use this equation to find Ft, the tensile force. Okay. So now the tensile working stress is equal to the tensile force divided by the area. Okay, just in terms of units. So to simplify things for you, let's say the tensile working stress, I used tensile working stress, I used 8 meganewton per meter squared. Okay, that's my units, assuming. So I'll input here 8 meganewtons per meter squared. What is it? Okay, 8. So the tensile force will be given here as well in newtons, okay, divided by the area. Now it is meganewtons per meter squared. Therefore, this area part, the values here which you use should also be in meters, okay? All right. Let's say, for example, for the tensile working stress, you use 8 newtons per millimeter squared, right? So the tensile force will be in newtons, and the area part, the units would be millimeters, okay? So that's about dimensioning. I mean, that's about units, okay? So how units affect your answer. Okay, so here, do calculations to find the height of the hub above the key. And make sure after you find that, add everything together and tell us what is the outside diameter of the hub. After that was the flange analysis. Okay, I would probably put here web analysis. No. Flange analysis determining the web thickness. Okay, how thick is the web? So again, torque. So we are assuming that the web will fail in shear. Okay, so it is, and wherever it interacts, wherever the flange interacts with the hub, that radius we are taking as the radius of the hub, right? The radius will always take it from the center of the shaft. Okay, the starting point is the center of the shaft. Do keep that in mind. So you find Fw, which is the force acting on the web. Okay, ooh, we have limited time. What else is left? So again, shear working stress, which is acting on the web, and the web is made out of cast iron. Okay, so the shear working stress here is 5 meganewton per meter square. Okay, so that's where you go. Shear working stress is in meganewtons, so the force should also be in meganewtons, right? Divided by the shear area, and area should be expressed in. So when you have units which are consistent, you'll see that they cancel each other out, right? Okay, and so shear working stress, you have, let's say you have expressed it in meganewtons per meter squared. So your FW has to be in meganewtons divided by meter squared, right? So after that, the shear area is equal to, as such, so the only variable left for you to determine is the thickness of the web, which is here, TW, right? And coming to the bolt analysis, so you could work either way. Either you could determine the number of bolts, or you could determine the size of the bolt. If you're determining the number of the bolt, start with the torque first. So torque is equal to the shear force divided by R, where R is half the pitch cycle diameter, right? In other words, the starting point for that R is the center of the shaft, and the end point of that R is to the center of the bolt. Okay, so that's half the PCD. So here you'll find the shear force acting on the bolt. Now TS is the shear stress acting on the bolt. So shear stress is equal to the shear force divided by the area. Okay, always remember that stress is equal to force over area. Okay. And in this case, what we are doing is we are multiplying the cross-section area of the bolt by the number of the bolt. So here it is where you can choose, right? So if you know the number of bolt, you enter that value in place of B and find RB, where, where R is the radius of the bolt. Or if you do know the radius of the bolt, then make B the subject of the formula, as is done here. Okay. So B is the subject of the formula. Shear force, you know, TS is the shear stress acting on the bolt multiplied by the area of the bolt. And as I said, area of the bolt is equal to, it is the cross section area, right? Pi R squared, where R is the diameter of each, the radius of each bolt. So that's your bolt analysis. So,
And so we will also be
yes,
assuming the web outside diameter, right? Which is 200 to 230 mm.
Yes. So just I'm given in red in front of you is the web. So the inside diameter of the web is equal to the hub diameter. The outside diameter of the hub, you can assume, right? So you can choose any, what did I say? Any value between 200 to 230, 240, even 250 is fine, right?
Okay, yeah.
Okay, that will help you with your drawings pretty much. So,
Sandeep,
yes.
one more question I would like to ask. Is there any interval for the radius of the bolt?
Interval, you mean
Or
to
we
say?
just choose by our own self?
Yeah, okay. So when you choose by your own self, you might have to do the calculations, repeat the calculations a number of times, right? The reason being, when you, let's say if you choose a value of R, and at the end, when you do, when you do calculations for B, and if you get a B as a very big number, like let's say, for example, if you get B as 10, then you know, okay, how can I fit 10 bolts in here, isn't it? Right? So then you'll have to go and change the R value again and do your calculations once more. So does that sound okay to you? No?
Yes.
Right, so that's what I'm saying. So you might have to keep changing the value of R. It's like changing up or down, okay? Until you get a value for B which is reasonable, okay, or realistic. So you want a value for B around 3, 4, or even 5, right? So that you have to play around with the value for the radius of the bolt, okay?
So we can just make R the subject in this case.
Which R? This one?
The bolt analysis one here.
Yeah.
Just like if we just want a reasonable bolt number,
Right.
so we can.
So no. If you want a reasonable bolt size or bolt number?
The number of bolts.
You can't make R the subject because once again B will also be the subject. So you'll have two unknowns.
Okay.
Yeah. So you either have, so whatever you're asking, Ibrahim. So if you can make B as 4 and then find R. So in your analysis, instead of determining the number of bolts, you are determining the size of the bolt, okay? So that's what I said. Either you could use whatever suits you, okay? If you want to find the size of the bolt, then you make R the subject here, which is this R I'm talking about. If you want to find the number of bolts, you make B the subject. Just do one, don't do both. Yeah, keep the questions coming in. So, let's see, Prashant, are you still here? Does this answer, I mean, I went over the bolt analysis again. Are you okay with this? So in case the Prashant is sending messages. Yes. Okay, that's good. So in case this session ends, don't worry, I'll restart it once more so that we can go over the drawings. Right. And when does it end? Oh, we have 3 minutes remaining. Actually, that should be enough for me to cover the. Okay, so when it comes to the drawing.
Sandeep.
Yes, sure.
One more question. The calculation sheet requirement is up till 3 to 4 sheets of calculation. What if it exceeds?
Exceeds, no problem at all.
No problem at all. Okay.
No worries at all. Right, as long as you're able to capture all the information, okay? Got it?
Yes.
That. Okay, now coming to the second part, which is the drawing generation. Right here, now you have done all the analysis, you know the dimensions of the key, you know the dimensions of the hub, you know the dimensions of the web, okay? Right, so you'll start drawing, okay? Now all of you are experts at AutoCAD by now, right? So things would be easy, you'll start. So it says here, you have to do detailed drawing as well as detail engineering drawing of your design and an assembly drawing. Okay, you know what assembly drawing is. And in a detailed drawing, what you can do is, detail means giving detail to your drawing, right? Okay, so make sure in detailed drawings you could have, I don't know, 2 pages of drawing, or where is it? So we'll start off with the shaft. Okay, then I haven't put the dimensions anything on it because that will give you the answer straight away. So this is what the shaft would look like. Give the diameter of the shaft, it's 48. Now as for the by how much you will extrude, that is entirely up to you. Okay, make sure you extrude the shaft greater than the length of the key. Okay, right? Okay, so it should look something reasonable. So put the dimension on this, and then okay, somewhere separate, draw the what's after the shaft, the hub. Okay, I've drawn it above it, so you can always separate this. Okay, okay, and then yes, dimension the inside diameter of the hub, the outside diameter of the hub. So how do you get the dimensions? That comes from a calculations. I forgot one thing, the key, isn't it? Okay, now the key is also there. There you go, that's the key. And dimension the key as well, the length, width, and the thickness. Okay, that's done for the key. What's next? Okay, then you have the flange. Oh, sorry, the web. Okay, then you dimension the web. What's the inside diameter? What's the outside diameter? So one thing I've missed out in my drawings. Okay, also dimension the bolt holes. You also have to show the bolts. Okay, you don't have to really show the what you call the threading on it. Just show a simple cylinder with a nut head. That's all. That will be the bolt. Okay, not the nut head, but the bolt head. So just show a simple cylinder which should be able to fit inside the bolt hole snugly, and show the bolt head. That's all. It could be a hexagonal bolt head. Okay. So are you guys okay with the drawing part? Or any questions? Okay, so that meeting ended, and back again. So we were discussing drawings, right? Okay, so fire away, right? Ask as much question as possible to clarify any doubts.
Sandeep,
Yes,
what's that purple part on top of the web?
the purple part is actually I just put it in a different color. That's just like the rim, okay? Yeah, the purple part is just this outside part.
Okay, so a bit
Yeah.
of creativity there.
Okay, yeah. So let's see if I'm able to orbit and show you what I mean by that. It's also part of the web, right? So no, not this. See, there you go. That's what it is, right?
Okay.
Yeah. So it's, I don't know why did I make it in purple? So better to.
It's okay. Purple is fine.
Okay, I know. Yeah, because maybe yeah, just to show. Yeah, yeah. If I put it in red, it looks it's a bit hard to see, right? So I just put it in purple. Right. So you guys have already learned about layers in CAD drawings, isn't it? So
This week's lab, it's about layers.
yeah.
Technical
So
lab
I used
documentation.
what I did was I used layers, so you can always give your layers names as well as different colors. Okay, so it's easy for to visualize, right? Rather than having everything in one color.
So,
So
sir,
yeah, Ibrahim.
the submission part of this assembly drawing, will it be in layout form or just in this model space?
Oh yes. Now I would prefer. See, so in layout that is where you create your pages, isn't it?
Yes.
So have two layouts, right? One for your detailed drawing, and the other one for your what's the other one? Assembly drawing.
Assembly. Yeah.
Yes. So in one layout you could have all your where is mine? Yeah, you could have all your drawings. In other words, you'll have a total of 1, 2, 3, 4. Yeah. So dimension them as much as you can, right? And the second layout, okay, is the second page, I would say, have your assembly drawing. Okay, you know how to put them all together, right? So it should look like that. If we assemble the whole flange, it will look something like that. So Ibrahim, does that answer your question?
Yes, sir. Thanks.
Okay, great.
Sandeep,
Yes.
is the assembly drawing simply like somewhat called the exploded one?
Exactly. Assembly exploded. Same thing. Exploded view.
Okay.
Yeah. Any other questions? And yes, always see, I have made many, it's like my model screen is a mess, right? Make a habit of doing this, because obviously when you go to your layout screen, you'll just be showing this, isn't it? With the paper, I mean, with the paper's correct paper size and what else is there? The title block and everything. But your model screen can always be a mess, right?
So, sir, just for clarification, so the detailed drawing will be all the parts separated with their dimensions,
With their
or
respective dimensions, exactly.
and assembly will be the exploded view of that.
Exactly, the assembly will be exploded view. So in assembly, try not to have those dimensions, okay?
Oh, okay.
Or you can always make a copy, just like I have done. Just make a copy of it. Put one as assembly, I mean exploded, the other one with all the dimensions on it, and just show it on the appropriate layouts.
Sandeep, for our detailed drawing, will we have it in the multi-view form or the solid 3D form? Like 2D or 3D? Like if you're doing detail, so we'll show the details in 2D or the 3D format.
Good question.
Because we'll also contain the dimensions, so I prefer 2D would be more detailed. I'm not know, but I saw it in the topic of the mechanical engineering. There was a sample drawing of the detail in the assembly drawing. So in that, the detail drawing was 2D.
Okay. Now, yes, but if you
Just take 3D.
yeah, if you because if you will be able to dimension this 3D, isn't it? It won't be hard, isn't it?
It won't be hard.
Yeah, in this case, what's happening is because they are not very complex dimensions. So for example, if you look at the key, you just have to do the length, width, and the height. So you can just dimension and just put
So
it
we
down.
just draw every part separately, and we just show
draw
that
every
dimension.
part separately and make sure it's on one page. I mean, in your layout. So if I go to layout 1, I should be able to see this and with all their respective dimensions, right? In the correct format dimension. So 3D is fine.
Okay.
So yeah, it will keep things simple for you guys, right? Any other questions? But yes, if you do, if you want to go ahead and do orthographics for your detailed drawing and put the dimension on it, you are very much welcome. Okay, right? But yeah, 3D with the dimensions, giving me the details, that would be fine. And the second one is just the assembly drawing.
Okay.
All right. Any other questions? Only two of your colleagues are asking.
And one more question, Sandeep.
Yeah, carry on.
For assembly drawing, that will be exploded on, right?
Yeah.
So for that, we'll have the labeling of the parts, like we'll have the balloon labeling, and we'll have the table for that.
Yeah, if you want, you could do that.
Okay.
If it's not done, I don't have a problem with it because the parts are all they are just 4 parts. Okay, so it will not be hard to identify. But yes, if you're able to give the table as well with the exploded and labeling of the each part, that would be really good.
Okay.
So
Sandeep,
yeah, yes.
4 parts not including the bolts.
Oh, sorry, my bad. Rafael, thanks for picking that out. You will also include the bolts as well. So in total, that would make 1, 2, 3, 4, 5. Yes, 5. Right, include the bolts as well. Big mistake there. So there will be 5 parts in total, right? The shaft, the key, the hub, the web, as well as the bolt. So if you're using 4 bolts, please show 4 bolts, okay? And as I said, for the bolt, a simple cylinder with a bolt head, okay? That would do, okay?
One more question.
Yeah.
Will this recording be posted on Moodle?
Yes, the other 3, yes, what I did, because the recordings are quite big, so I have posted I've uploaded the recordings on YouTube and given the link on Moodle. This last one will be done as well. So probably by the end of this day.
All right. Thank you very much.
Yeah. Any others? So there's Jacob here, Jessica, Kavinesh. Kavinesh is really quiet. And Molly, Mulo, and Nitendran, Ruben. And by the way, coming to your midterm reports, so what you would be, if you have submitted, or whoever has submitted from your group, okay, wherever you submitted your assignment, below it there's a comment. So we have all commented on your respective reports. Okay, this is in regards to the project. Okay, so the midterm report you submitted, so we have commented if there are any changes needed or if everything is fine. Okay,
You mean the feedback is already out?
yeah, the feedback is already on. Yeah,
Okay.
under the submission, under the file you submitted. Any other questions before? So this is the last Zoom session by me, okay, in regards to everything for your tutorial. And when it comes to tutorial, the 4 sessions we had for the Zoom, so that was the tutorial for week 12 and week 13. Week 13 is next week, isn't it?
Yes.
Yeah.
Yep.
So just coming back to the purple part which is attached on the web.
Yeah.
So the thickness is assumed for that, or?
So what I did was I used the same thickness which we calculated for the web. I used the same thickness for the purple part as well. It's like a rim, okay?
Oh, okay.
So that's the rim. So yeah, but it is also part of the. It is part of the. It is part of the web.
And so its extrusion is also assumed.
That extrusion, yes, you can assume. I had to assume that as well.
Okay.
But make it something which looks reasonable.
Yeah.
Yeah. But it will be, that purple part will be extruded more than the web itself, right?
Uh-huh.
Yeah. It's like this, yeah. Any other questions?
Sandeep, one more question.
Yeah.
About the scale, will we use any particular scale for the drawings? No.
No, it does not specify, so you have the freedom to choose your own scale, okay? In this.
Okay.
Yeah.
For the web.
No, for your drawings.
Oh, sorry,
Yeah.
my bad. Okay.
Yeah. This is one of the simpler ones, okay? They are, yes, for your assignment too.
For last year, they had something different, huh?
Yeah.
Like they had the handle one.
Yeah, that's a bit complicated. The last year was a bit, but the principle is the same. The calculation, the torque, and all the analysis is the same.
Yeah.
But yours is this year. It's pretty much straightforward.
Straightforward.
In the terms of this. Actually, the answers are. I mean, 3/4 of the work has been done for you in these PowerPoint slides. All
Pretty
you need to do is,
much.
all you need to do is pick out the formulas, input the numbers, and get your dimensions. And the only thing you will be doing on your own, make sure you do it on your own, okay? Is getting the drawings in. Right. I don't think you need any more Zoom or live sessions for this one, okay?
So I think that's well explained enough for us.
Okay. And I know because you guys are also busy with other things, other courses as well. So thank you for all your time. So that is where I will end for today. Okay. And yeah, I'll try my best by the end of the Friday, which is today. I'll try to have this video out, okay, on YouTube. Right. Okay, so stay safe, and if anything else, you can always drop me a message on Moodle, or you can always email me as well, right? And I will be happy to respond to your request. Okay. So yes, okay. See you when I see you in person.
Oh, Sandeep.
Yes, yeah. If you like to leave, you're free to leave. I'll be here for a while.
Thank you.
That's all.
Yeah.
Oh, I thought you were wanted to ask me something. Okay, yeah. Thank you too.
Sandeep.
Yeah.
One more question I have. Regarding this, regarding this scale, like if a scale is given, like this is a separate question from the assignment.
Yeah.
I'm just clarifying it. Like if a scale is given for a particular drawing, like say for example 1:1, right?
Yes.
So we go on the model page and we change the page setup. The scale we change to 1:1. And what about the layout page? Do we have to do the same on the layout page, or because when you go on the layout page, there is a hidden line on the page. So when you enlarge that black border, that hidden line still remains. So
yeah, this one.
Yeah, this one, the hidden line.
Okay, let me try this out. Right, page setup manager. What do you use? Modify.
Yeah.
Just guide me through. Right, then you choose a printer. Okay, let's say I just choose any printer. Then you choose the paper size.
That's it. A4 297 by 210.
Just A4. Yeah. And all of this is, what do you use a scale here? 1:1, eh?
1:1.
Yeah, 1:1. Okay. And then that's all, eh? And then
that's all.
Okay.
Yeah, that's for the Moodle page. No, you did it on the layout page, right?
Yeah. But we don't do this on the model page. We only do this on the layout page because see, the model is like a sketch. It's like a canvas.
Okay.
You don't really need to do that for the model.
So just do it on the layout page.
Yeah, just do it on the layout page, and then you. Hey, where's my drawing? And then you do this part, which is. You know, you have to drag out. Where does it-
Yeah, that part is fine. I just wanted to
Yeah.
clarify about that scale. Thank you.
So you got it, eh?
Yeah.
Yeah. So
Yeah.
you go inside the, what you call that, and then you
Viewport.
change your scale. Yeah. Viewport, exactly.
Okay. So thank you so much, Sandeep.
Okay, no problem.
Sit.
So I just had a lab question, which is
Yeah,
for
carry on.
this week.
Huh.
So there we had to do an orthographic projection. So sir, for that it was specified to use the layers, but sir, can we also use the base command, which is on the top right of this menu table?
The
So when you
screen.
use the base command, then all of the top view, end view, and the front view is automatically done, and the layers are also automatically shown.
Yeah, then that should be fine.
Okay, okay,
Yeah.
sir.